Welcome to today's session. We're diving into LeetCode problem number 606, construct string from binary tree. In this problem, we'll explore how to traverse a binary tree and construct a string representation of its structure. Let's walk through the steps and strategies together, and by the end, you'll have a clear understanding of how to tackle this challenge. Let's get started. In this problem, you are tasked with constructing a string representation of a binary tree using a pre-order traversal. The string must follow specific rules to capture the structure of the tree. First, the root node's value is always included in the string. Then, if the left child exists, it should be enclosed in parentheses. If the left child is absent but there is a right child, you must include an empty pair of parentheses to indicate the absence of the left child. For the right child, if it exists, it should be enclosed in parentheses as well, but if it is absent, no parentheses should be included at all. The input is the root of a binary tree, where each node contains an integer value and pointers to its left and right children, which can be null. The output is a string that represents this tree structure based on the given rules. Let's look at a concrete example. Suppose the input is a binary tree with the structure 1, 2, 3, 4. Visually, this tree can be represented as, the root node 1 has 2 children, 2 on the left and 3 on the right. Node 2 itself has a left child, 4, but no right child. Starting with the root node, the string begins as just the value of the root, so we start with 1. Then, we process the left child of 1, which is node 2. Since node 2 exists, we enclose it in parentheses, giving us 1, 2. Next, we move to the left child of 2, which is node 4. Again, since node 4 exists, we add it with parentheses, resulting in 1, 2, 4. Finally, since node 2 has no right child, we don't add anything further for the left subtree of the root. Now, we move on to the right child of the root, which is node 3. Since node 3 exists, we add it in parentheses, appending 3 to the string. Combining everything, the resulting string representation of this tree is 1, 2, 4, 3. This captures the entire structure of the tree where the root, left subtree, and right subtree are all represented based on the rules. Another example involves a tree with the structure 1, 2, 3, null, 4. In this case, the tree can be visualized as the root node 1, which has 2 children, 2 on the left and 3 on the right. Node 2 has no left child but has a right child, which is node 4. Starting again with the root node 1, the string begins as 1. For the left child, which is node 2, we add it in parentheses, giving us 1, 2. However, since node 2 has no left child, we must include an empty pair of parentheses to indicate its absence. Then, we add node 2's right child, node 4, in parentheses, resulting in 1, 2, 4. Finally, we process the right child of the root, which is node 3. Since node 3 exists, we add it in parentheses, giving us 3. Putting it all together, the final string representation of this tree is 1, 2, 4, 3. For a simpler example, consider the case where the input tree is just a single node with the value 1. Since the root node has no children, the string representation is simply 1. This is the most straightforward case, as there are no subtrees to process. Keep in mind the constraints of the problem, such as the tree having up to 10 to the power of 4 nodes and node values ranging from -1000 to 1000. Additionally, edge cases like left-skewed or right-skewed trees must be handled carefully. For example, in a right-skewed tree, empty parentheses must be included for each missing left child. Constructing the string efficiently for large trees is also crucial to ensure the solution meets the problem's requirements. To solve the problem of constructing a string representation of a binary tree, we explored a few approaches. One straightforward method is the brute force approach, which relies on a plain pre-order traversal. The key idea here is to traverse the tree, appending the value of each node to the string while adhering to the problem's rules for parentheses. For example, a node with both left and right children would be formatted as the node's value followed by its left and right subtrees enclosed in parentheses. Special care is needed when a node has only one child. If it has just a left child, only the left subtree is appended, but if it has only a right child, we must still include empty parentheses for the missing left child. While this approach is intuitive and simple to implement using recursion, it has a significant drawback. string concatenation in Python is inefficient for large inputs because strings are immutable. This can lead to a worst-case time complexity of O(n squared), making it less suitable for larger binary trees. To address the inefficiency of the brute force method, we considered an optimized approach that still uses pre-ordered traversal but improves performance by leveraging list-based string building. The idea is simple yet effective. Instead of directly concatenating strings during the traversal, we use a list to accumulate the components of the string. Lists in Python are mutable, making operations like appending much faster. The parenthesis rules for constructing the string remain the same as in the brute force approach, but the key difference lies in efficiency. By appending values in parentheses to a list during the traversal and joining the list into a single string at the end, we achieve a linear time complexity of O(n). This approach also has a space complexity of O(n), accounting for both the recursive stack and the list used for string building. Overall, this method strikes a balance between simplicity and performance, addressing the inefficiencies of the brute force solution. Another approach we examined was an iterative method using a stack. Instead of relying on recursion, this approach simulates pre-ordered traversal explicitly with a stack to manage the nodes. The iterative method avoids potential issues with stack overflow that can arise in deep binary trees when using recursion. However, handling parentheses correctly becomes more intricate in this implementation, as the traversal logic must account for when to open or close parentheses based on the node structure. While the time and space complexity of this approach are comparable to the optimized recursive solution, it introduces additional complexity in implementation. This makes debugging and maintaining the code more challenging, especially for those less experienced with iterative traversal techniques. Ultimately, the iterative approach is functional but sacrifices readability and simplicity for a similar level of efficiency. The breakthrough insight in this problem was recognizing the performance cost of string concatenation in Python and finding a way to mitigate it. Using a list to build the string incrementally avoids the inefficiency of repeatedly creating new string objects. Another key detail was handling nodes with only one child. Ensuring that the output includes empty parentheses for a missing left child while omitting them for a missing right child was essential to comply with the problem's requirements. When comparing the approaches, the brute force method is conceptually simple but inefficient for large inputs due to its O(n squared) time complexity. The iterative approach is efficient but introduces unnecessary complexity. The optimized recursive approach, on the other hand, achieves O(n) time complexity while maintaining a clean and straightforward implementation. By balancing simplicity and performance, this strategy emerges as the ideal choice for solving the problem effectively. In this problem, we are tasked with constructing a string representation of a binary tree using pre-ordered traversal. The structure of the string follows specific rules. Parentheses are used to enclose child nodes, and for a node with only a left child, we omit any parentheses for the right child. Additionally, if a node has no children, no parentheses are included at all. To solve this, we start by defining the input and output. The input is a binary tree where each node contains an integer value and pointers to its left and right children. The output is the string representation of the tree, formatted according to the rules we've discussed. The problem lends itself naturally to a recursive pre-ordered traversal approach. This means we visit the root node first, then recursively construct the string for the left subtree, followed by the right subtree. For our recursion to work, we also need a base case. If the current node is null, we simply return an empty string. To implement the recursive case, we begin by converting the current node's value to a string. If the node has a left child, we recursively build the string for the left subtree and wrap it in parentheses. If the node has a right child, we do the same for the right subtree. However, if the left child is null but there is a right child, we include empty parentheses for the left child before appending the string for the right subtree. This ensures the structure of the tree is accurately represented. Finally, we concatenate all these parts together and return the resulting string. To put this into code, we define a recursive function tree to a CR. If the root node is null, the function returns an empty string. Otherwise, we initialize the result with the string value of the current node. If the node has a left subtree or a right subtree, we add the string representation of the left subtree wrapped in parentheses. This step ensures that even when only the right child exists, the absence of the left child is explicitly noted. Next, we handle the right subtree. If the current node has a right child, we append its string representation wrapped in parentheses to the result. This completes the recursive construction of the binary tree string, which is then returned. The key insight here is that we use a recursive pre-order traversal to construct the string. Starting with the root, we process the left and right subtrees recursively, ensuring the tree structure is faithfully represented. Parentheses are used judiciously. For a node with a right child, we include empty parentheses for the left child if it's null, while no parentheses are added for leaf nodes. Additionally, the use of Python f-strings makes string concatenation both clear and efficient. The algorithm relies on the binary tree as the input data structure and constructs the output as a string. By leveraging these simple yet powerful operations, we can solve the problem in a clean and efficient manner. Now, let's consider some edge cases to ensure our algorithm handles all scenarios correctly. If the tree is empty, meaning the root is null, the function should return an empty string. For a tree with a single node, the output is simply the node's value, with no parentheses included. For a node that only has a left subtree, we omit the right child's parentheses entirely. Conversely, if a node has only a right subtree, we include empty parentheses to explicitly indicate the absence of a left child. Moving on to complexity analysis, the time complexity of this algorithm is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once, and string concatenation is performed in constant time for each node. The space complexity is O(h), where h is the height of the tree, as the maximum depth of the recursion stack corresponds to the height of the tree. With these considerations, we can confidently handle all tree structures and ensure our solution is efficient. Let's walk through an example to solidify our understanding. Consider this binary tree. The root node is 1, with 2 as its left child and 3 as its right child. Node 2 has no left child but has a right child, 4. Starting at the root, we add 1 to our result. Next, we traverse the left subtree of node 1. At node 2, we add 2 to the result. Since node 2 has no left child but has a right child, we add empty parentheses followed by 4 to represent its right subtree. Returning to the root, we now traverse its right subtree. At node 3, we simply add 3 to the result, as it has no children. Combining these parts, the final output string becomes 1, 2, 4, 3. This example demonstrates how the algorithm accurately constructs the tree's string representation while adhering to the rules for parentheses placement. This code solves LeetCode problem 606, construct string from binary tree, by recursively converting a binary tree into a string representation using pre-order traversal. The tree2str function is the core of the solution. Here's the breakdown. 1. TreeNode class. A basic TreeNode class is defined with val, left, and right attributes to represent each node's value and its children. 2. Base case. The function first checks if the current node, root, is none. If it is, it returns an empty string because there's no value to process. 3. Node value conversion. For non-none nodes, the function converts the node's value to a string and initializes the result variable with it. For left subtree processing, the function recursively processes the left subtree. Parentheses are added around the left subtree's string representation if the left child exists or if the right child exists. This ensures that the parentheses are correctly included even when the left child is absent but the right child is present. 5. Right subtree processing. The function recursively processes the right subtree. Parentheses are added around the right subtree's string representation only if the right child exists. This avoids unnecessary parentheses when the right child is absent. 6. Result construction. The processed results from the left and right subtrees are appended to the result string, maintaining the correct format. 7. Output. The final string representation of the binary tree is returned. This approach ensures that the tree is traversed in pre-order fashion and that the output string adheres to the specified rules. The code handles all edge cases, including nodes with only one child, and ensures optimal recursion. Here, we start by defining a basic structure for our binary tree using the TreeNode class. Each TreeNode object has 3 fields: val, which stores the value of the node, and left and right, which are references to the left and right child nodes, respectively. We also provide three constructors, one with no arguments, one that initializes only the node's value, and another that initializes the value along with the left and right child nodes. Moving on to the solution class, we define the method tree2str, which takes the root of the binary tree as input and returns its string representation. The first step inside this method is to handle the base case. If the root is null, meaning the tree or subtree is empty, we simply return an empty string. If the root is not null, we use a string builder to start building the result string, appending the value of the current node as the first part of the output. Next, we handle the left subtree. If the left child exists or if the right child exists, we include the left subtree's string representation within parentheses. This ensures that the correct structure is maintained even for cases where the left child is null but the right child is present. We achieve this by recursively calling the tree2str method on the left child and appending the result inside parentheses. After processing the left subtree, we move on to the right subtree. Here, parentheses are added only if the right child is not null. Just like before, we use a recursive call to tree2str to generate the string representation of the right subtree, appending it within parentheses. Finally, we return the complete string representation of the tree by converting the string builder object to a string. This approach ensures that the tree is represented accurately while adhering to the required format. Here, we are working with a simple binary tree where the root node has the value 1, and it has two children, 2 on the left and 3 on the right. We start at the root node, initializing our result string as 1. Since the root has a left child, we process the left subtree by recursively calling the function on the node with value 2. At node 2, we initialize the result as 2. Since it has no children, we simply return 2. Back at the root, we append the left subtree result inside parentheses, making the result 1, 2. Next, we notice that the root also has a right child, so we process the right subtree recursively at the node with value 3. At this node, the result is initialized as 3, and since it has no children, we return 3. Finally, at the root, we append the right subtree result, updating the result to 1, 2, 3. The final output for this tree is the string 1, 2, 3. Now, let's look at an example where the binary tree has a missing left child. Here, the root node still has a value of 1, but it only has a right child with the value 3. We start at the root, initializing the result as 1. Since there is no left child, we explicitly add empty parentheses to maintain the correct format, so the result becomes 1. Then, we process the right subtree recursively at the node with value 3. At this node, we initialize the result as 3, and since it has no children, we return 3. Back at the root, we append the right subtree result, updating the result to 1, 3. The final output for this tree is the string 1, 3. Finally, consider a tree where the right child is missing. The root node has a value of 1 and a left child with the value 2. Starting at the root, we initialize the result as 1. Since the root has a left child, we process the left subtree recursively at the node with value 2. At this node, we initialize the result as 2, and because it has no children, we return 2. Back at the root, we append the left subtree result inside parentheses, updating the result to 1, 2. Since the root has no right child, there's no need to add parentheses for the right child. The final output for this tree is the string 1, 2. From these examples, we can observe that parentheses are always added for the left child, even if empty, when there's a right child. However, parentheses for the right child are skipped if it's absent. This recursive approach ensures that the tree is processed in the correct order, producing a properly formatted string. To analyze the time complexity of the tree2str function, let's focus on the recursive traversal of the binary tree. The function visits each node exactly once. This happens because, for every node, the function is called recursively on its left and right subtrees, ensuring all nodes are processed. At each node, we perform a constant amount of work, like converting the node's value to a string and concatenating strings with parentheses. While string concatenation depends on the length of the resulting string, the overall traversal ensures that each node contributes only once to the processing time. Therefore, the dominant factor here is the number of nodes in the tree, denoted as n. This determines the time complexity of the function, which is O(n). In the best case, if the tree is empty, the function returns immediately with an empty string, resulting in a time complexity of O(1). However, for any non-empty tree, whether balanced or unbalanced, the function must visit every node, making the average and worst-case time complexity O(n) as well. Now let's consider the space complexity. This is influenced by two main aspects: the recursive stack space and the memory required for constructing the output string. First, the recursive stack space depends on the depth of the recursion, which corresponds to the height of the tree, denoted as h. In the worst-case scenario, where the tree is highly skewed, the height is equal to the total number of nodes, n, leading to a stack space usage of O(n). In the best case, for a perfectly balanced binary tree, the height is proportional to O log n. Second, the function builds the output string incrementally. The memory required for this string is proportional to the total number of nodes, or O(n), since each node contributes to the final result. When combining these two factors, the overall space complexity in the worst case is O(n), as the skewed tree maximizes both stack usage and string size. Even in the best case, while the recursive stack may only require O log n space, the string construction still dominates, keeping the total space complexity at O(n). When comparing approaches, a brute force method might involve generating strings for all possible subtrees and then combining them repeatedly. This would result in redundant calculations, leading to an exponential time complexity of O(2 to the power of n). Such an approach is highly inefficient due to the combinatorial explosion of subproblems. In contrast, the optimized approach we use here employs a recursive traversal, ensuring each node is processed only once. By constructing the output string incrementally and avoiding redundant computations, we achieve a time complexity of O(n), which is far more efficient. To summarize, the optimized solution has a time complexity of O(n) and a space complexity of O(n), which accounts for both the recursive stack and the output string. This approach is optimal for the problem, minimizing both time and space usage while avoiding unnecessary work entirely. When working on this problem, there are a few common mistakes that can trip you up. First, not handling null nodes correctly is a frequent issue. For instance, if the left child is missing but the right child exists, you still need to include empty parentheses for the left child. Failing to do so would result in incorrect output. Always review the rules for when parentheses are required to ensure the structure is accurate. Another mistake is overcomplicating the traversal logic. Many people try to construct the string manually in a way that becomes unnecessarily complex. Instead, focus on using a clean recursive traversal and let the recursion naturally build the string. Finally, avoid using unnecessary data structures like additional stacks or lists to store intermediate results. These can increase the complexity of your solution and introduce bugs. Stick to either a simple recursive approach or an iterative traversal with a single string builder to keep things efficient and clean. Another pitfall to watch out for is inefficient string concatenation in loops. Directly appending strings inside recursive calls can cause performance issues because string operations are immutable, which means new strings are created each time. To optimize this, use a string builder in Java or list-based concatenation in Python, as these are much more efficient. Additionally, many people overlook edge cases during testing. It's important to test scenarios like trees with only one node, trees with just left or right children, and even empty trees to ensure your solution is robust. Deeply nested trees should also be tested, as they can expose performance bottlenecks or recursion depth issues. Preparing for these edge cases will help you avoid surprises and demonstrate thoroughness in your approach. Understanding the nuances of this problem can provide valuable insights for interviews. This is a classic recursive tree traversal problem, so recognizing the pattern of pre-order traversal and the specific rules for parentheses placement is critical. Interviewers often use edge cases to test your attention to detail, so be ready to explain how your solution handles them. The optimal approach here is usually a recursive one, as it aligns naturally with the structure of the problem. While iterative solutions can be used to showcase versatility, they are less common in practice. One of the most important aspects in an interview setting is to communicate your thought process clearly. Walk through how you address null nodes, where and why you include parentheses, and how you optimize for performance. This clarity will not only demonstrate your technical skills but also your ability to articulate solutions effectively. To deepen your understanding and expand your skills, it's helpful to explore related problems. For example, LeetCode 144, Binary Tree Preorder Traversal, shares the same traversal pattern and is excellent for practicing both recursive and iterative methods. LeetCode 257, Binary Tree Paths, is another similar problem, but it focuses on constructing strings to represent paths in the tree rather than the overall structure. LeetCode 543, Diameter of Binary Tree, is a different type of tree problem that emphasizes traversal and handling null nodes effectively. Finally, LeetCode 94, Binary Tree Inner Traversal, is a foundational problem that strengthens your grasp of general tree traversal techniques. Working through these problems will reinforce your understanding of tree structures and traversal strategies. There are alternative approaches to solving this problem, each with its own trade-offs. The recursive approach is often preferred because it is simple, intuitive, and aligns naturally with the hierarchical structure of trees. However, it does have a downside. For extremely deep trees, it can lead to stack overflow due to excessive recursion depth. The iterative approach, on the other hand, avoids recursion and is better suited for very deep trees, but it is more complex to implement and requires careful management of a manual stack. Another consideration is how you handle string operations. Using a string builder in Java or list concatenation in Python is significantly more efficient for larger trees, as direct string concatenation creates unnecessary overhead. Choosing the right approach depends on the specific constraints of the problem and the scenarios you want to optimize for. Great work! Today, we reviewed how to construct a string from a binary tree using preorder traversal. We discussed key considerations like handling parentheses and edge cases, and analyzed the algorithm's efficiency. Keep practicing tree traversal problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!